Hello everyone, I am Dr. Munish Bharadwaj from School of Engineering and Technology of IGNOU. Today we will be discussing concrete mix design. Till this stage, we have discussed the properties of various ingredients of concrete. Now these ingredients, as you know, are used for making the concrete. But for making the concrete, we have to have proper proportioning of different ingredients of the concrete. So this is the basis of today's discussion, that how these ingredients are proportioned to make the quality concrete and also to get the target strength of the concrete. So let us first see what are the objectives of mix design. Why we should go for mix design? Mix design is done to achieve a minimum compressive strength at 28 days period based on the value assumed by the designer. First, the designer will assume that what compressive strength is to be achieved for concrete at 28 days. The concrete mix should be cohesive for preventing the possibility of honeycombing and segregation. Meaning that there should not be any honeycombing or the segregation in the concrete. So our concrete mix should be cohesive. The provision of sufficient workability for obtaining 100% compaction with the available compacting equipments. That whatever equipments are available for compaction, we should achieve the full compaction. So that much of workability should be there in the concrete mix. Then next criteria is durability. Durability, which is associated with compressive strength. The greater the strength, more will be the durability of the concrete. The mix should be designed to achieve the desired strength in the hardened stage. That after hardening, the concrete give the required strength. The mix should be designed in such a way that the minimum quantity of cement is used, as it is the costliest material. You know that in cement concrete, cement is the most costly material, so it should be used in minimum quantity, and by using this in minimum quantity we should get the optimum strength or the maximum strength to achieve satisfactory appearance. Also, this our mix should be that after hardening it should give a good appearance, aesthetic appearance. Now there are different type of mixes, and out of these, first let us consider the ordinary concrete mixes. Ordinary concrete mixes or the nominal concrete mixes are made without preliminary test. In ordinary concrete, no trial mixes are done in the laboratory. These concretes are used when use of controlled concrete is not practicable. Ordinary concrete are of grade M10, M15, M20 and M25. So these are the grades which are considered in ordinary concrete mixes. Ordinary concrete mixes offer simplicity, and under normal circumstances they have a margin of strength above that specified. What is the meaning of that? That here the concrete mix will be having little more strength than the specified one. If we are saying that we are preparing the 20 Newton per mm square or 20 MPa concrete, then it will be having little bit more than the 20 Newton per mm square strength. And also it is simple to make the ordinary concrete. Nominal mixes do not account for the varying characteristics of the concrete materials and may result in under or over rich mixes. You know that in nominal mixes we are not accounting for the variations in the characteristics of the ingredients. So our concrete mix may be either maybe under rich or over rich. Means it may be having less cement or more cement. The nominal mix is expressed in terms of aggregate cement ratio by volume generally. Bulk density has to be considered in case of weigh batching. If, as you know that there are two methods, volume batching and the weigh batching. If we are going for the weigh batching, then bulk density has to be considered while doing the concrete mix. In selecting the ratio of fine to coarse aggregate, suitable modifications or adjustments have to be made. Now, second type of mix. So till this we discussed about the ordinary or the nominal concrete mix. Second type of mix is design mix. So design mix depends upon the type of cement, quality of the fine and the coarse aggregate, and amount of water used. So these are the factors which governs the quality of the design mix. The other factors like the workability, compacting equipments, curing methods adopted, etc. have to be considered before arriving at the mix proportion. This method also does not guarantee the correct mix for the design strength, though the figures are arithmetically correct. Means that we have done the mathematics correctly, our calculations are correctly for the design mix, but there may be chances that we may not get the correct mix for the design strength. The design mix will serve as a guide only, and trial mixes are essential before ensuring that we have achieved the desired strength. So this is the importance of trial mixes here. Steps of design mix. First step in the process is crushing strength of concrete. First step is to fix the average crushing strength of concrete for laboratory conditions. The concrete mix shall be designed for greater strength than required because the working conditions in the field are not controlled as in the laboratory. You know that in field the control may not be as good as we can achieve in the laboratory. The IS code specifies that the crushing strength for which the mix should be designed in the laboratory should be 1.25 times the strength actually required. Now, next is water cement ratio. The ratio of minimum quantity of water to the weight or volume of cement required for obtaining a consistent and workable concrete mix is called water cement ratio. Water requirement may be expressed as number of liters of water required per bag of cement. Here you see in this table the crushing strength of concrete and water cement ratio. If we look at the crushing strength in kg per centimeter square after 28 days of curing, in next column you will find the water cement ratio, and this water cement ratio here in the table is given for both if you are going by weight or if you are going by volume. So for both in the two columns this is given, and in next column quantity of water in liters per bag is given. So let us look first. When the crushing strength in kg per centimeter square is 530, water cement ratio by weight is 0.35, by volume we will be taking is as 0.5, and for this water cement ratio the quantity of water in liters per bag of cement will be 17.5 liter, and the mix that we will achieve will be dry mix. If we go to the serial number 5, then here the crushing strength is 320 kg per centimeter square, water cement ratio by weight is 0.55, by volume it is 0.79, and quantity of water in liters if we consider for per bag of cement is 27.5 liters, and the mix that we will achieve will be a workable mix. Another example, you go to the serial number 10. Here the crushing strength is 180 kg per centimeter square, water cement ratio by weight is 0.8, and by volume it is 1.14, and quantity of water in liters per bag of cement will be 40 liters, and the concrete mix that we will achieve will be wet mix. So this way you have this table, and for different crushing strength of concrete after 28 days of curing, different water cement ratio you will be using, and you will see that what type of mix you can achieve. Now next step is fixing slump for the mix. After fixing the water cement ratio, the next step is to fix the workability of the concrete, because as you know that our concrete should be workable. So it is done by slump test or compaction factor test. So by any of these tests you can fix the workability of the concrete. Here you see in this table permissible slump values in mm for various concrete works. If you see slump in mm, if it is 0 to 25 mm, the corresponding compacting factor may be 0.78 to 0.85, and the degree of workability of this mix will be defined as very low to low, and the uses for which the concrete is suitable will be vibrated concrete in roads where powerful vibrating equipment can be used, then vibrated piles, then you can use it for precast beams and railway sleepers, and similar works where high strength is desired. Next, if you look at the slump value of 25 to 50 mm, the corresponding compacting factor will be 0.85 to 0.92. The degree of workability for this mix will be low to medium, and this mix can be used for roads with ordinary forms of vibrating and finishing machines and manually operated compactors. Also you can use it for mass concrete foundation without vibrating equipments, and also simple reinforced sections with vibrations. So these are the situations where you can use this mix. If slump value is 50 to 100 mm, the corresponding compacting factor is 0.92 to 0.95. The degree of workability will be defined as medium to high, and the situations where you can use this mix is high tamped roads with slump 50 to 75 mm, also for normal reinforced work without vibration, and heavily reinforced sections with vibrations. If the slump value is 100 to 180, then corresponding compacting factor will be more than 0.95. The workability will be high, and the situations where you can use this concrete is for sections with congested reinforcement, other works where placing is difficult, not normally suitable for vibration. So these are the situations where this type of mixes can be used. Now next step is fixing nominal size of the coarse aggregate. After fixing slump for the mix, the next step is to fix nominal size of coarse aggregate for making concrete. Here you see in this table the nominal size of coarse aggregate for various concrete works. Nominal size of coarse aggregate in mm, it is given in the second column. If it is 15 mm, then suitable concrete works will be reinforced cement concrete lintels and slabs of thickness 50 to 120 mm, and posts and the battens which is having a cross section area of 40 cm square. The nominal size of coarse aggregate of 20 mm is suitable for unreinforced cement concrete work between 50 to 150 mm thickness, conglomerate floors, reinforced cement concrete works exceeding 120 mm but not 450 mm. If nominal size of coarse aggregate is 40 mm, then it can be used for concrete mix, which can be used as unreinforced mass cement concrete works on small jobs over 150 mm for reinforced concrete over 450 mm. If the nominal size of coarse aggregate is 65 mm, then unreinforced mass concrete work on ordinary works. Now let us see the proportioning of aggregates. After fixing the water cement ratio, slump and the nominal size of aggregate, the next step is to determine the economical proportion for coarse and fine aggregate. The methods adopted for proportioning of aggregate are arbitrary method, fineness modulus method, White's method, etc. Determining the quantity of cement paste. This step consists of preparing a number of batches of combined aggregate in fixed proportions. In each batch, varying quantity of water cement paste having fixed water cement ratio are added to get the required slab. Now let us see the methods of mixed design. What are different methods of mixed design and how the mixed design is done? For the given concrete materials, the various factors to be considered in specifying a concrete mix are water cement ratio, then cement content or cement aggregate ratio, the gradation of aggregates, and consistency of the fresh concrete. In general, all these factors cannot be chosen arbitrarily. Usually 2 or 3 of the factors are specified and other factors are adjusted to give minimum workability and economy. These 2 criteria has to be considered, and as I told you just now that 2 to 3 factors will be specified and others will be adjusted accordingly to achieve this workability and the economy. The requirements are usually dictated by general experience with regard to structural design conditions, durability and conditions of placing. Water cement ratio express the dilution of the paste. Cement content depends upon the amount of paste, that how much amount of paste is required for making the concrete. By varying the amount of given fine and coarse aggregate, grading of aggregate is controlled. Means you can control the grading of aggregate by varying the amount of the fine and the coarse aggregate. Consistency depends upon the practical requirement of placing of concrete. Means where the concrete is to be placed, in what conditions the concrete is to be placed, that will govern the consistency of the mix. So let us see the methods used for proportioning. The following methods are used for proportioning: arbitrary proportion method, maximum density method, fineness modulus method, White's method, Tablot Ricard method, trial and error method, American Concrete Institute mixed design method or ACI method, Road Note 4 method, and IS code method, that is according to IS 10262. So let us first look at the arbitrary proportion method. The method of grading of aggregates arbitrarily is known as arbitrary or specific mix method. In this case, arbitrary proportions of different ingredients are taken as 1 part of cement, 2 p part of fine aggregates and 2 p part of coarse aggregate, all by volume. Means if we are taking this in the ratio of 1 cement, then p amount of fine aggregate and 2p amount of coarse aggregate. Means fine aggregate and coarse aggregate will be taken in the ratio of 1:2. So that way you see here p and 2p. So by doing so, you will get the different proportions, such as if we put the value of p as 1, then 1:1:2. If you put the value of p equal to 2, then you will get 1:2:4. If we put the value of p as 3, then you will get 1:3:6. So likewise 1:4:8, etc. In general, always coarse aggregate are taken twice the fine aggregate, as it is clear from that p and 2p terms. Maximum density method. This method is economical to design for a minimum amount of cement water paste in a concrete mix. Fuller assumes that the greater the amount of solid particles that can be packed in a given volume of concrete, the higher will be its strength. So this is the assumption of the Fuller. In this method, the aggregate should be graded in such a way that the mixture attains the maximum density. And Fuller suggests suggested curves for this purpose, which are based on this equation P equal to 100 into small d upon capital D to the power 0.5. Here capital D is the maximum size of the course aggregate, P is the percentage of total material smaller than the size small d, where the small d is maximum size of the fine aggregate. So this way Fuller suggested the curves which are based on this equation. The drawback of this method is that the effect of particle interference is ignored in this method. The aggregates graded to give maximum density results in harsh and unworkable mix practically. The workability can be improved only when there is excess of paste above that required to fill the voids in the coarse aggregate. Let us see one example here. Suppose it is to be desired to grade a mix with 20 mm maximum size coarse aggregate and 4.75 mm fine aggregate. Then the value of P in that equation will be, means that percentage of material finer than 4.75 mm will be given by P equal to 100 in small, here the value of small d is 4.75, value of capital D is 20. So here we will be putting these values. So then P will be equal to 100 into 4.75 upon 20 to the power 0.5. So if we get 48.73. So roughly you can say 50%. So means the percentage of material finer than 4.75 mm in our mix will be 50%. So this is the meaning of this calculation. Now let us move to the next method, which is fineness modulus method. The index number which describes the relative sizes of coarse and the fine aggregate is called as the fineness modulus. The fineness modulus is determined separately by sieving coarse and the fine aggregates through the following set of sieves. If you are going for finding the fineness modulus of coarse aggregate, then IS sieve used for these coarse aggregate will be 80 mm, 40 mm, 20 mm, 10 mm and 4.75 mm. If you are going for finding the fineness modulus of the fine aggregate, then IS sieved used will be 1 mm, 600 micron, 300 micron, 212 micron, 150 micron and 75 micron. So by using these sieves you can find the fineness modulus of coarse aggregate and fine aggregate separate. And here this P value will be given by x minus z upon z minus y into 100. What are these x, y, z? X is the fineness modulus of the coarse aggregate, y is the fineness modulus of the fine aggregate, z is the economical value of fineness modulus for combined aggregate, means by combining the fine and the coarse material, coarse aggregate. So this formula will fix the proportion of fine aggregate to the coarse aggregate, means from this formula you can find the percentage of fine aggregate that is to be used, and percentage of the coarse aggregate to be used you can get by subtracting this value from 100, means percentage of coarse aggregate will be equal to 100 minus the percentage of the fine aggregate. Here this table gives you the economical value of fineness modulus for combined aggregate. You saw in that equation there is a term Z. So this is the table that will give you the value of the term Z. For example, for the particle size of 20 mm, the fineness modulus will be minimum 4.7, maximum 5.1 and average fineness modulus will be 4.9. So that way you can get the different values of Z for different particle size. With high water cement ratio, lower value of fineness modulus should be adopted, and with lower water cement ratio, higher value of the fineness modulus should be adopted. The next step is to find out the quantity of water cement paste which is to be added to the fine and the coarse aggregates in order to obtain the required workability. The slump test is used to confirm the quantity of water cement paste. The method consists of preparing a number of batches of combined aggregate. Combined aggregate means fine aggregate plus coarse aggregate in the fixed proportion. In each batch, varying quantity of water cement paste having fixed water cement ratio are added to get the required slump. In order to start with, the minimum quantity of water is added in the first batch. Thereon, we will be increasing the amount of water. It is determined from the following formula, that is 0.3p plus 0.1y plus 0.01z into W by C into P. P is the quantity of cement by weight, Y here is quantity of fine aggregate by weight, and Z is the quantity of coarse aggregate by weight. And as you know, W by C is the water cement ratio. Now let us see the next method, voids method. The principle involved in this method is that the voids in the coarse aggregate are to be filled in by the fine aggregates, and the voids in the fine aggregates are to be filled by the cement paste. As such, it is necessary to determine voids in fine and the coarse aggregate. So, volume of fine aggregate required for 1 cubic meter of coarse aggregate will be equal to total voids in coarse aggregate plus 10% aggregate extra to allow for additional voids created by wedging action. So, this way you can calculate the volume of fine aggregate. Volume of cement paste required for 1 cubic meter of coarse aggregate will be equal to total volume of voids in the fine aggregate plus 15% used in 1 cubic meter of coarse aggregate extra to allow for additional voids created by wedging action. So that way you can find the volume of cement paste. Then volume of dry cement will be calculated by multiplying the volume of cement paste by 1.2. Means the volume of dry cement will be 1.2 times the volume of the cement paste. Now for determining the percentage of voids, aggregates are filled up to the top in a vessel of known volume, and this vessel measured volume of water is poured in order to fill it. Then the percentage of voids will be equal to measured volume of water added into the vessel divided by the total volume of aggregate filled in the vessel into 100. So that way you can calculate the percentage of voids. Now let us see another method, Tablot-Ricart method. This method is based on the experimental investigations in which the compressive strength of concrete was found to depend upon cement space ratio, and it is given by cement space ratio equal to CSR equal to C upon C plus V. Here C is the volume of cement solids and V is the volume of water plus voids per unit volume of freshly made concrete. So that way you can get the value of cement space ratio. This method is not popular as it requires more laboratory work. It also does not take into account the water cement ratio law as the basis of strength. This method involves complicated calculation work and trial mixes to achieve a workable mix. So that way it is not popular. So this way we have discussed what is concrete mix, how it is designed, what are different methods for design. Some of the methods we have discussed in this video, some other we will be discussing in the next one. Thank you for watching.